So, this course is on physics of turbulence. So, we will discuss physics aspects. Okay. So, I will describe bit of it in today's class. So, let me just first describe what is turbulence problem, at least from the course perspective. Okay. So, first, why study turbulence? So, I am going to show you that turbulence is a very important process for a lot of applications, including what happens in day to day life. So, let us take this example of a room heater. Okay. So, we have this heater in the left and you are here in a cold winter night. So, you come close to the heater, want to warm yourself. Now, let us say the distance is 1 meter. Now, we want to solve this problem. How long will it take for the heat to reach you? That is what we want to solve. So, the important, well, one obvious way to solve this problem one would attempt is start with the diffusion equation, right. So, this is a diffusion equation. So, theta is temperature, this is temperature, and kappa is a thermal diffusion coefficient. So, heat diffuses by this kappa. Okay. Now, this I think everybody knows about this equation. So, one important point to remember is that this equation has exact solution. So, we can solve this exactly by Fourier series. In fact, Fourier gave the first solution for this equation, but we will not solve it exactly in today's discussion. We will just do order of magnitude estimate. So, I would like to, I am interested in approximate time, I am not really interested in exact solution. So, I can just take this first part, this one. So, this has magnitude theta by t, t is a time scale. Okay. So, t is what I am looking for, how long will it take for the heat to travel 1 meter. Now, the second term also I will do order of magnitude estimate. So, dimensionally theta will go at the top, grad is 1 by L. So, that will be 1 by L squared and kappa. Okay. So, here theta cancels and we get basically equation for t. So, which I am going to write in the next slide, but we need this parameter kappa. No, I know L, I am looking for t, but what is kappa? And kappa can be looked up in your book on statistical physics. Kappa for thermal diffusivity in air is 10 power minus 5 meter square per second. Okay. We can also derive it from kinetic theory, but we will not get too much into that aspect, we will just use this as a parameter. So, T will be L square by kappa. So, what is the number? So, just plug in L is 1 meter. So, 1 meter square by 10 power minus 5 meter square per second, that gives you 10 power 5 seconds. It is way too long. Okay. Now, I can't wait for 10 power 5 seconds to warm myself up, right. So, this is totally wrong, right. This, in fact, the whole calculation is wrong, is contrary to what we experience in daily life. Now, in fact, this is one example, but we can also think of diffusion. No? So, diffusion of perfume, how long will it take to diffuse 1 meter, and analysis is exactly same, except kappa will be replaced by diffusion coefficient, which is again roughly same order of magnitude. So, what has gone wrong? So, what has gone wrong here is that I am missing one important term in this equation. Okay. So, the term which is missing here is the fluid property of air. So, in this room right now molecular diffusion is not dominant factor for transmission of heat, for the transmission of rather of dust particles or so on and so on. Okay. So, what is important, which I am going to show you in the next slide, is this new term u dot grad theta. Okay. So, this term is coming, u is the velocity of air, local velocity of air. Now, so this is a realistic equation. Okay. So, my diffusion equation is not the correct description. Now, we like to see, well, you may say how big is this term compared to kappa grad square theta. So, I can do again order of magnitude estimate. No? So, u dot grad theta by kappa grad square theta. So, theta will cancel, 1 grad will cancel, but this is not exact calculations, but these are often done in fluid mechanics. So, we can get a number, in fact this is very commonly used. So, this is U L by kappa, right. So, there is a lot of cancellations. Now, what is U for typical air in this room? So, for example, I mean I would say I will estimate from cigarette smoke, you have to just look at concentratedly with some focus, find that it will probably travel in 1 second 10 centimeter, okay. But it could be faster too. I mean this is only a magnitude, order of magnitude. So, this is U is 0.1 meters per second. I am using only MKS right now, or SI unit. L is same 1 meter and kappa is 10 power minus 5. So, the number is 10 power 4. So, what does it mean? The term U dot grad theta is 10 power 4 times bigger than diffusion term. In fact, this number we will also discuss later, is called Peclet number, okay. But we will discuss that later. So, what will time depend on? Time diffusion is too small. So, I can ignore this term and I can equate these two, just equate these two and you will get estimate for time. In fact, you can easily see what the answer should be. So, I should equate d theta by dt or this partial theta partial t to U dot grad theta. So, from this again same order of magnitude estimates. So, theta will cancel and t will be L by U, which is 10 seconds. So, this is correct estimate, okay. So, what has helped diffusion for heat is the flow term. Now, we will discuss it later. I am using only L as capital L, which is large length scale 1 meter, but if you look at air, which I am going to show you one slide bit later, that there are structures within structures. So, we are looking at only one scale, which is largest scale, and at that scale we get this equation, okay. Now, we can also, well, I will discuss that bit later, okay. So, there are processes happening at each scale, at different length scales. Now, so what do we learn from this example? So, fluid flow is important to study, okay. We can't simply use thermodynamics blindly, and this process is not only in air like in stars, planets, this term or terms like this play important role. So, I just want to summarize this lessons learned from this example is the flow term is very important, and this is what we will focus in this course. So, this is what I would like to say, this dust particle in the room is advected by U. So, this example given in textbooks that you look at the dust particle motion inside the room, it is not by diffusion, not the Brownian motion, that is not the random walk, it is by U, it is contrary to what is taught in textbooks. And Brown's experiment, in fact this experiment, of course we believe that, it is not that Brown was, but this experiment was done in still water, where the U is 0 or U is very close to 0. So, number, the Peclet number for the experiment for Brown would be close to 0. So, the nonlinear term can be dropped, or Brown could drop the nonlinear term, he did not need to worry about it, okay. But many experiments or real life scenarios or even astrophysical scenarios, that U dot grad theta is important, okay. So, it can't be ignored. And one important point, so this is which we will discuss a bit later, that this mixing with diffusion term kappa grad square theta was very slow, but what made it more efficient or what made it faster, this mixing, was the U dot grad theta term, and that in fact is the turbulence. So, the term which I told you, U dot grad, so the ratio I call it Peclet number, nonlinear by viscous diffusion term, it is like Reynolds number, okay. So, Reynolds number is told up for the velocity field, Navier-Stokes, but this is like Reynolds number for scalar quantity. If that term is bigger, the Peclet number is bigger than 1, much bigger than 1, then it is turbulent, okay. So, that nonlinear term which is much bigger than the diffusion term is improving mixing. Right now mixing of heat. Okay, is that clear to everyone? Okay. So, other examples, I mean I will give only couple, I mean the turbulence is everywhere, this is quite true. So, atmosphere of planets and stars, so you will most of the time the Reynolds number or the nonlinear term compared to diffusion term is very large. So, weather, climate, diffusion and pollution, this plays a big role. Interior planets and stars. So, this is atmosphere which is normally considered to be the upper part of the planets or star, but interior you go inside inside the earth there is a part where the Reynolds number is quite large and magnetic field is being generated in that region, okay, it is called outer core, and there too things are turbulent. Industrial applications, there are huge applications. In fact, most of these appliances like air conditioner, there will be turbulence inside, okay. When the steel is being formed in furnaces, flow is highly turbulent, okay. So, all of astrophysics, galactic, planetary environment, we need to study this. It turns out that it is very difficult, I mean some of it we do not know how to solve it, there are only order of magnitude estimates, and for example, the magnetic field generation, which we will cover some of it in the class, in the earth or in sun, that remains to be unsolved problem. We understand some of it, but not all of it, okay. And one simple reason is that one way to express this is that linear equations have exact solutions, but nonlinear equations that do not have exact solution most of the time. Some special ones have, but most of the time you do not have exact solution, and there is no generic property that this, like Laplace equation, there is a certain property, but not for nonlinear equations, okay. So, let us now I will state, now I hope we kind of motivated enough to see that is an important problem. So, we will see what is the problem, okay. So, we are, so in this example I will just say that we are looking for this Navier-Stokes equation, okay. So, I am just illustrating my Navier-Stokes equation. So, this u dot grad u, so this is a nonlinear term like similar to u dot grad theta, this pressure gradient, I am going to describe it bit later, but I just want to give you some idea, this forcing and this is a viscous term, okay. So, we will discuss in more detail, but I just want to tell the problem, what is the turbulence problem, okay. So, these are various terms, and this is a picture of vorticity, magnitude. So, what is vorticity? Is curl of u and its magnitude. So, this is also important quantity which we will discuss in this course. So, here we have, you can see the structures probably not very clearly, but there are bigger structures here and there are smaller structures, then the still small structures and small structures. So, the structures of different scales. So, this curl of u, so it is not homogeneous. Normally we assume that density is homogeneous, but this is not homogeneous. So, it is multi-scale problem, that is one important point, is a multi-scale problem, and we will discuss it bit later, that dissipation occurs at a smaller scale. So, you also, so something happens at very small scale, small scale are important, it is called singular problem, okay. So, length going to 0 you need to consider properly. So, this viscous term is important, this plays a very important role, but some phenomena happens at large scale, some happens at small scale. So, there is a lot of interscale interactions. So, this problem which we will study in this course, equation is known, but solution is not. In fact, I will just state one of the problem which can give you $1 million if you solve it. It is called one of the millennium problems, there are 7 millennium problems, and this is for Navier-Stokes, or in fact for Euler problem. So, prove, so this P is missing here, prove or give counter example of the following statements, okay. Okay, so this is getting cut. So, basically given the velocity field and scalar field, oh, so this got cut. So, So, I will, so this equation is not coming out right. So, the question is whether there exists a solution for Navier-Stokes or not. We do not even know there exists a mathematical solution. Finding it is different matter, but prove the existence of a solution. So, by the way, not every equation has a solution. There are equations for which in ODEs we know, ordinary differential equations we know, there are conditions for having a solution. There are some equations do not have solution. So, it is not even clear Navier-Stokes equation has a solution or not. So, this $1 million prize is for proving there exists a solution. You do not need to find the solution, but just prove that there exists a solution, or if it does not exist, then you show that it does not exist. Okay. So, this is a statement. Of course, this is what applied mathematicians are working on, not my field. And so, you can see is I mean, even we do not even know that there exists a solution. Okay. And this problem is basically at small scales. This is a singular problem. Nu tending to 0 is a big issue. Okay, so I will go to the next slide, which is physics approach, which is what we will do in this course. So, basically here in physics we will, like other parts of physics, we analyze the data from experiments and simulation and come with general theories. So, I will construct theory from first principles, that is my objective. Okay. I will, well, we have succeeded only to some degree, not a lot. I mean, not a lot of unsolved issues remain, but there are some models which are derived from first principles, they are not models. So, engineering there are a lot of models, you build a model which will from the data fit, but these are derived from the first principles. Okay. That is what is the difference. So, these are theories. So, as I said, there are only handful of theories. Kolmogorov theory is one of them. In 2D turbulence we have some theories, but there are very few for turbulence, and we will cover some of this in this course. So, I will also tell in this class that though we are looking for universal theory, so this one fashion in physics is called look for universal theory, and Newton's law is universal, right. Newton's law F equal to ma works for all mechanical systems. So, we want to consider a law which will work for all turbulent systems. Okay. In fact, so that is a dream. In fact, that is what people want to state, the universal law of turbulence. But it turns out my experience for last many years is that there is no universal theory of turbulence. If I put forces, then law changes quite a lot. There are some basic tools, but law changes dramatically. So, for example, for hydrodynamic turbulence without any external force, so that Fu term was, you set it to 0. Then there is a law. Kolmogorov theory is basically F is 0 in the inertial range. But I do another system like heat the fluid from the bottom, then we have buoyancy. Then my law changes dramatically. It is not the same law. If I put rotation, then the law is also very different. If I put a magnetic field, then in fact we get a different behavior. So, it looks like this problem, in fact lot of problems in nature, the equation may be the same or equation may have slight difference, like Schrodinger equation. Schrodinger equation is same, of course the potential term is different for different systems, but if you put different potential I get a different solution or different system. So, there is no universal theory even in quantum mechanics. You have one equation which works for many systems. Similarly, here we have one form of equation where Fu is, I can change force, but saying that I look for a universal theory, well I am one of the, many people believe there is universal theory, but I think they are all wrong. Okay. So, there is no universal theory for turbulence. They are good common tools, but not universal theory, one theory for everything. Okay. Also boundary condition. So, we will see some examples like walls. If you put walls in the side, then physics is very different. So, like convection we heat from the bottom, that has walls have very important effects like channel flow. So, that also has significant effects. Okay. So, So, as I said, there is no single universal theory of turbulence, and we need to so I mean if there is no one single theory, does it mean that we do not even attempt this problem? No, we should attempt, but we should understand different aspects of the different phenomena or different forces. Okay. So, this is what we will do in this course. We will develop general tools, but then we will apply this tool to different systems and try to derive properties of those systems. I will tell you some very nice tools which we will employ for studying all these systems. I may not cover in big detail, but we will cover in some detail the basic aspects. So, this is look for common tools and apply them to variety of problems. So, this is what I like is called energy flux. So, one example which is given is that you take a bucket of water, water, and stir this water by a rod. So, I supply energy at what scale? I am forcing it. So, I am supplying energy at large scale, bucket scale, and this water will flow down, this energy will flow down to small scale, correct, flow down to small scale. So, there is a transfer of energy from large scale to small scale. So, this is called energy flux in turbulence language or in this field. It is not like flux of electromagnetic radiation. So, that is energy transferred per unit area per unit time. No? So, that is very different thing. The energy flux is energy flow across scales, okay, and there is a way to quantify it, and that is what I will show in this course, how to quantify this energy transfer. In fact, I may have this next line. So, we will describe various. So, this is one tool, but we will also have other tools. One example which I like to give. So, before I go, so I like this example of finance model. Okay, so there is a interesting connection. So, what is finance model? So, there is a money supply by the central government. No? So, this basically they distribute budget. So, they get money from elsewhere, but they basically supply money to. So, how do they supply? They give to states, states to districts, districts to blocks, village. So, it flows from large scale, which is the government scale, the central government scale, to small scales. So, this is, but it is a multi-scale problem. It is not a single scale problem, and it is not flowing in real space. It is really flowing across scales. Okay. So, you should not visualize this in real space. If you see visual in real space, you cannot get this flow. So, this is in fact very natural in Fourier space. Fourier decomposes different scales, which what we will do. So, it is basically a multi-scale problem, and this is analogy. The money flow is like energy flux. But I also want to make a remark that in lot of physics, like for thermodynamics, is there a flow of energy across scales, or what are the scales in thermodynamics? Actually,
bulk area, so scales are large scale.
No, thermodynamics is basically hinging on molecular interparticle collision length. So, it is the temperature is defined as average quantity, but there is only one scale, length scale, which is mean free path length. Okay, and there is a, so you can look at, is there a energy cascade or is there energy flow? So, if I look at one region of here in real space, but there are many ways to define. Okay, so you can look at molecules here. The number of molecules are approximately same as molecule at different times. Okay, now let us focus on only one region. Let's think of a region like this. Number of molecules on the average do not change, and energy coming in and energy going out should be equal. There is some energy flow in and out, but there is no net flow of energy at any scale. In fact, you can look at small scale, large. In fact, there is no scale, there is only single scale. It is a single scale problem, and there is no energy flow from one scale to other scale. So, it is an equilibrium system. Equilibrium systems do not have this transfer from one scale to other scale, but this turbulence is a non-equilibrium problem. There is a supply at the scale and there is a dissipation at the scale. It is a very different system, but there are other systems in physics. There By the thermodynamics, according to me, in this room is not really applicable. We define temperature, of course, but this room is a non-equilibrium room. It's not, thermodynamics plays a small role, important role but small role. But earthquake is an example of non-equilibrium systems, money supply as I said, or biological systems. It takes energy, then does things, it is all non-equilibrium systems. So, there are, I mean, these are requires different tools, and the tools of thermodynamics do not work in many of these applications. Okay, what about engineering approach? So, this approach is quite different. So, I start with an example, of course very important. I mean, this is in fact they really do much more things than what physicists can get to. So, let us take an example, make an aeroplane, working aeroplane. So, this is what I want to do, and if you succeed, then you make a efficient and safe aeroplane. So, this is one objective which the engineers achieved. So, Wright brothers, by the way, they did not really get the aeroplane by accident. I mean, if you really see, this story is really inspiring. So, they were not from MIT or Harvard, they had a shop, but they had set up their own wind tunnel. Everybody knows what is wind tunnel. So, some of you, the physics students, may not know. So, wind tunnel is, so I need to see whether aeroplane will fly or not. So, people do experiments in IIT itself. I mean, this kind of, there is a wind tunnel aerospace department, the big tube, that is the wind tunnel. So, wind tunnel will have this tube. Okay, I really can't draw this well, and one end of the tube has this grid. Okay, so this grid is one end of tube. Is that clear? And you push air from the left, very high, fast speed air, and you put aeroplane in here. Okay, this put small aeroplane. You can't put a big aeroplane. You put a small aeroplane, and then we can make measurements of this on this aeroplane. So, you can make measurements on the stresses on the wings, how much lift is there on the wing. So, all these experiments are done with small aeroplanes, and there is interesting property of Navier-Stokes equation. If you can measure the forces and so on this small plane, then you can extrapolate for the same Reynolds number to large aeroplane. Okay. So, this is called self similarity. Okay. So, this some of it you have learnt in your other course which I taught myself. Okay. So, this self similarity. So, you can extrapolate the forces on the large aeroplane, and they are doing all these experiments in their small garage. Okay. And so, but they are not looking to solve turbulence problem. Please make sure. These physicists are trying to say, well, what is the force from the first principle, what are the properties. They want to say, well, I want to make an aeroplane, flying object. Okay. So, objective is different, a working machine, of course with lot of intuition. So, it requires big knowledge of fluid mechanics. It is not that you just put the model and it will work. This design, there are infinite number of ways we can make wings, but you should have intuition to make a good wing which will work. So, look for solution. So, one thing will be first design and order of magnitude estimates. So, this is really plays a very important role, order of magnitude estimates. So, how big it should be, if it is too tiny then there will not be enough force. So, all that stuff, order of magnitude. And then we do experiments. I mean, so the engineer will do experiments. For example, this is wind tunnel experiment. Okay, for various designs. To make the real one takes money, huge money and also effort. So, idea is to make small experiments, then make a big one, make several big ones and see which one works best. Also, nowadays this computers have become very useful. Earlier they were not, they were not very heavily used. I mean, Wright brothers did not have a computer. Okay, computers came much later in 1950s, but now it is heavily used. In fact, I am told that Boeing has, the number may be wrong, but they say that equal money for experiment and equal money for simulations. Huge amount of money goes into simulations, and in fact, Indian spacecrafts or rockets, they use the simulations to see whether how would this, well, I don't know say what missile, this all these things will fly, rockets or aeroplanes. Okay, so this is very important for engineers also, and physicists we rely heavily on computer simulations for understanding the flow and making models. But you can see the approach is different. They are not looking for first principle theories, but it is not that everything is just guesswork. So, there are simulations, you need to solve the Navier-Stokes equation. So, I want to solve flow around aeroplane here, and the Reynolds number for the aeroplane could be large near the wings, it could be 10,000. Now, if I do first principle calculation, I require very big grid, which we will estimate in the course bit later, but we do not, I mean, if you do that much grid, it will take years of computer time. So, these guys will basically use various models. So, the viscosity term, the nu grad square u, this was the term, if you recall, nu grad square u, this is viscous term. So, typically they alter this nu. So, say I am not interested in small scale, but I am looking at large scale nu. So, there are various models. In fact, the Reynolds stress model will help you to model nu for realistic flows at large scales or large eddy simulation. This is one simulation, one tool. So, this is also used for modeling nu. Okay. So, we will do some of it. So, but you can see the idea. So, this first principle calculation is not what engineers are interested to solve. Well, by the way, engineers also come in different variety and physicists also come different variety. So, some engineers are interested in first principles, okay, they are basically should be in physics department in some sense, and some physicists are working on all this stuff. So, it is now a mixed, a lot of interdisciplinary and cross talks, but to make this model of Reynolds stress we require this first principle theories. So, these theories are built typically by physicists. So, this connection, and then of course innovated by good numerical scientists. Okay. Is that clear, the connection, I hope. So, first principle theories are important to construct these models. KFCL model is directly from Kolmogorov theory, this one, but it helps you to model the flow. You do not need to start from first very fine mesh, and you do not need to really solve all the scales. So, this helps you in efficient numerical schemes, so which is practical for weather simulations. If you really want to do this called direct simulation, where you do not want to make a model, then it will be grid which will be bigger than the best supercomputer of today. Okay. So, we can estimate bit later, but it is really impossible to do direct simulation of the earth. In fact, it is somewhat meaningless, we do not really, it is so complicated, the terrain is complicated, ocean has a lot of stuff. So, people make large scale simulation. So, the grid is not millimeter, grid is kilometers. So, a grid size is kilometer, not millimeters. For direct simulation, of course, we need millimeter, but whether it is kilometer. So, we need to of course work with this various parameterization, and so typically these are not first principle calculation. So, this is the first major difference. So, they are physics approach and engineering approach. Okay. But of course, both are important. So, please do not misunderstand that I am trying to put down one or the other, and it is very important to cross talk, and this in fact fluid mechanics is a field which is very practical. So, people really cross talk. So, any fluid mechanics meeting if you go, you will find physicists, engineers, atmospheric physicists, meteorologists, engineering of course various types, mechanical engineer, aeronautical engineer, chemical engineer, then there will be astrophysicists who will be there. So, this is, and mathematicians, there is some applied mathematicians will. So, this is really mix of various sorts of people. Okay. So, I kind of gave you the picture of what different people do. Mathematicians, they will look for properties of Navier-Stokes. they will not be too worried about real plane and so on. So, idealized system, boundary condition, idealized. Physics will make a model, which is like periodic box, but still viscosity is important. So, get some data. Engineer will make real objects, and try to model flow around aeroplane. Chemical engineers very important. Why? Because mixing. So, all these chemical processes, mixing is very important for them. So, chemical engineering turbulence is very critical for a lot of this process mixing in chemicals. Okay, so important things. So, from these examples we can see the experiments are important, numerical simulations are important, also order of magnitude. So, many of these will be just order of magnitude estimates. Okay. Since we really do not have exact solutions, so we make some order of magnitude estimates, and many times they work, but approximate, they work. And so, these two experiments and simulation, they complement each other. So, what do we mean by that? So, so there is example of liquid metals. What is liquid metal? Like molten iron is an example of liquid metal. You have seen this movie Terminator. So, Terminator is a liquid metal. So, this is a robot which is made of liquid metals. So, liquid metal experiments, we can reach very high Reynolds number, we can apply magnetic field. So, we can do many interesting aspects with that. So, in fact, car plates, before the surface of car, so it is molten and they apply some magnetic, they do various processing. But unfortunately, so if I want to see what is turbulence inside, we can't see inside a metal, it is opaque. So, it is not like water, you can see inside, air, water. So, then we are basically lost. So, we will do ultrasound. Okay. So, this ultrasound is done for this. So, this is for these objects, we can't see inside, so we do ultrasound. But simulations become very handy for this. So, I can see inside. Okay, I can get velocity field anywhere in the flow. But the problem in simulation is that we can't reach very high Reynolds number. Okay. So, which we can get in experiments. Experiments can go up to 10 power 8, 10 power 9 Reynolds number. Simulations struggling at 10 power 5. Okay. So, these are plus points and negative points. So, in fact, they are really complementary and people do both. Convection, there are lots of stuff experimentalists can't do, but we can do in simulations. But we can't reach the Rayleigh number or Reynolds number which experiments can reach. So, these are complementary data we get from these two important aspects of fluid mechanics. And I would also say that numerical simulation is more like an experiment, we treat this as an experiment. So, basically I am not able to get this from experiments, real experiments. So, then we say, well, let us do simulations. So, and then based on the data we make models or try to make first principle models. Okay. And as I said, order, this is important aspect and you should learn this one. Okay, so these are some of the references. So, this book which is not in print, but I will give you the PDF right now. This is in print. So, we will use some of this instability calculations. Okay, I will do in midway of the course, maybe third week or fourth week, and there are quite a few other books, but I think these two also will use some of it. Okay, if I do not use it, but you can have a look. This book by Pope and Lezour, and I think that is it for today. Thank you.